Alright. Hi guys, welcome to another stream in electric drives. I tried to make this the last stream in the electric drives. Okay, so the last video covered chapter 3 from 1 to 3:3. So now this video will cover from 3:4 to 3:8. Okay, so we are still on electric braking. That's what we are still doing. Electric braking, right? So now I said we know that we perform braking under two conditions, right? The first is when we are lowering a heavy load, we perform braking, or second, when during stopping. So the last time we took while lowering a heavy load, and we saw regenerative braking for that. We saw rheostatic braking for that and plugging for that. Okay. So now we're still looking at the same thing. We are looking at, but except we saw regenerative braking in DC shunt motor separately excited. So now we're looking at regenerative braking in DC series motors. Regenerative braking in DC series motors. So that would be from 3. So it start from 3. But let's look at it from the bottom here. So let's look at the circuit for doing that. Okay. So this is a circuit. This is what we use here. So the goal is that, or the aim, or what we do is that, in order to perform regenerative braking in a DC series motor, we must first convert it to a separately excited motor. And this is a circuit that helps us to do that. And I realize that when I open S1, when I open this S1 here, okay, and when I close this S3 here, current will flow through this path. Current will flow through this path. This path here. Oh, sorry. Current will flow through this path here. Because now here is closed now. This path here. Right. So I'll have the armature current flowing through the armature here. Now, don't forget that there was some current flowing through the RF before I opened this S1 here. Now this diode will ensure that the current to flow through the diode here comes through this RF here until I close this S2, where now I can have the field current flowing through the field. So the process is to open S1 and close S2 and close S3, and I'll close S2, so I can have it now as a separately excited motor. Okay. So that's it. That's all you must know on the other side. So kindly take your time to do the reading too. Okay. Now, when we come to the rheostatic or dynamic braking of the DC series motors, it's basically the same as the DC shunt motors too. So here, so you connect an external resistance to ensure the current remains in the same direction, right? And here, the resistance you connect, you must ensure that when you add the field array, the armature resistance and the external resistance, it should still be less than the critical angle. Okay, it should be less than the critical angle. All right, sure. So you know how these are by now. That for bidirectional, we know that these are the same thing here, right? For say the motor was initially moving at this region, right? And then I apply the regenerative braking. I apply regenerative braking. If it's a bidirectional load torque, what will happen? You know that the torque becomes negative, right? Torque becoming negative implies that the current is negative, but don't forget that the E remains positive still. Okay, yeah, and then speed 2 remains positive and other things. So that's what this means here. So we realize that for bidirectional, let me see. Okay, this supposed to be negative here. This current must be negative here. So that's the first thing I can say. That has to be negative. And then everything else is correct. Okay. So that's it. So over here, the formula still holds. We know that the formula, this formula here, the formula omega for rheostatic braking, omega is equal to what? Minus REX over K phi squared times TE. This formula still holds. Okay, this formula still holds in this. Okay, let's move on. Okay. So let's go ahead and look at this question. This question says that a DC series motor is subject to rheostatic braking against a load torque of 318 Newton, 318.3 Newton meter. Determine the value of the resistance to be reconnected in the motor to limit the speed to 480 R per minute. The total resistance of the armature and the field is 0.24, and the open circuit characteristics corresponding to the 900 rev per minute is gotten as this, right? Now what you must know is that in this question, okay, here's what we want to find. I'm supposed to find the resistance that I'll connect. So let me call it the REX, right? Let me call it the REX. So let me say I know that resistance, total resistance is given by what? E over IA, right? I know E is equal to what? E is K phi omega over IA. So what I want to determine from this is I want to determine K phi. So first I'll plot two graphs, torque against IA, and I also plot K phi against IA. So say I get a torque against IA to be this, K phi against IA to be this, right? Kindly pay attention. Okay. So what you'd expect is that now the torque they gave me, see they gave me the torque to be 318.3. So for that torque, I'll locate a corresponding IA. Let me call it X. And then I'll come and trace that IA to find the K phi, the value of K phi. And that's the K phi that I'll use in what I wrote here. I wrote total is K phi omega over IA. So at this IA value here, all right, I'll find some corresponding K phi. Then multiply by the speed. The speed is at 480 r per minute. So I'll put that 480 r per minute here, change it to rad per second, and then that will give me the R total. And once I have the R total, I can go ahead and subtract. You see, they gave me, I know that R total is made up of what? It's made up of RA, RS plus REX. So they gave me the sum of RA and RS. So I will subtract it from the R total to get my REX. So that's what we want to do. So that's the whole concept. So let's see how. So now, you see in the question, I was given IF against E, right? They gave me the field current against the EMF. So they gave me, so you can read here, gave me IF against E. So IF was 20, 40, 60, 80, 100. The E's are 261, 540, 738, 882, 945. Right. What you must know is that, so I said I want to plot IA against K phi and IA against E. So I need IA. What you must know is that because it's a series motor. Series means that the field, right? The field winding and the armature are in series. Are you following? This means that the current going through the armature, which is IF, is the same as the current that going through the current going through the field IF is the same as the current going through the armature IA. So here my IA is the same as my IF. So my IA will also be 20, 40, 60, 80, 100. Now the next thing I must find my what? K phi. K phi, right? Let's call it K phi that I'll use to plot. So now, so I say, well, we know that E is equal to what? E is equal to K phi omega, right? E is equal to K phi omega. So from here, K phi is equal to what? K phi is equal to E over omega, right? Now, don't forget that we're told that the open circuit characteristics was obtained for what? 900 rev per minute, right? So for 900 rev per minute, and for every E, I'll find the K phi value. So that's what I'll do. So let me find it. So this means that I'll do E over omega is what? Omega is 900, right? So let me change it to times rad. So 2 pi over 60. And that's 30 pi. So I'll do E over 30 pi. So the first E will be 261 over 30 pi. And that value will be 2.768. I'll put it here. Then I'll do the next, which is 540 over 30 pi. 5.7. So I'll use to fill this side. Then when I come to my torque 2, I know that torque is equal to what? Torque is equal to K phi IA. So this K phi I found here, I multiply by this IA. So here over here, I'll get 55.36. I'll get 229.09 and so on and so forth. So once I have my TE, I can plot TE against IA, as I said here. Plot K phi against IA here. Then I'll find the IA for the torque they gave me, 318.3. So I'll find the current corresponding to that torque here. And then once I have that current, I can put that current here to find the K phi corresponding. So now I can now use my RTS K phi omega over IA. Omega is the 480. Omega is the 480 rev per minute. K phi is the K phi I'll find for the graph, and IA is the IA I'll get here. So that's it. So that's how you go about this work. So kindly take time to go through. So that's what was done in this experiment. That's what was done in this experiment. So you just have to understand what was done. Okay. So the next is plugging. Okay. So plugging can be done so the plugin, okay. The plugin can be done in two ways, right? The first way is that, so we know that this is series, the characteristics looks like this. So the first way of doing plugin is that I can connect a very high resistance that causes characteristics to look like this here. And once this happens, for unidirectional low torque, the plugin can occur here, right, in quadrant 4. But the second thing is that I can reverse the EMF. Reverse the EMF always rotates this through 180, so the graph comes somewhere around this region. And that can be used to stop a bidirectional low torque. So that's it. That's it. Okay. So kindly take time to do the reading. But that's it for like this side. Then this is how the connection is done. So you kindly take time to read this part. Okay. So let's try our hands on this question. Let's try our hands on this question. The question says that what? A 220 volt 20 kilowatt DC shunt motor running at this speed is to be braked by reverse current braking. The armature resistance is 0.1 ohm and the rated efficiency of the motor is 88. Calculate the resistance to be connected in series with the armature to limit the initial braking current to twice the rated current. Okay, so you know that this is a what kind of braking? Reverse current braking was applied. So you know that initially it's motoring, right? So let's find the rated current first. So initially it says moving like this. Then when I apply the reverse current braking, characteristics becomes this. So it moves from here to here. Say operation 0.1 to 2. So first thing is for us to find the rated current, right? So it says that we want to find the resistance that will limit the initial braking current twice the rated current. But in first, what's the rated current? We've been given voltage, power, and efficiency, right? So now I know that efficiency is what? P out over P input, right? They're giving me the output power of the motor as 20 and efficiency. So let me find the input power. That's the electric power drawn by the motor. That's efficiency. So that will be output power, which is 20 kilowatt as they gave us, over efficiency 0.88. That will give me 22.72 kilowatts. So this is the electric power drawn by the motor. So I know that P is equal to what? Ivan, right? So from here I can find the I. I hope I'm making sense. Then the I is equal to what? I is equal to P over V. I is equal to P over V. So that's how you find your. So I is equal to P over V, right? So I know that my P is 22.7, which is the P electrical PI, times 10 exponent 3 over V. V is 220. So when I compute this value here, I'll get I to be 103.6 amps. So that's my I. So I is 103.6. Right. Okay. Now they say that I want to limit the current at this breaking point to twice its value. So let me call it my IA2. IA2 become what? 2 times 103.6. We want it to be twice. This will give me 206.12 amps. Except don't forget that because it's occurring at this region here, it becomes negative. So let me make it negative 206. Now we know that at this region during the breaking, I know that the breaking current IA2 is equal to what? Minus V minus E over, I'm looking for RA plus RB. So I want to find the RB. That will make this IA negative 206. So that's all here. So I'm having what? I'm having negative 206 is equal to minus V. V is 220 minus E over RA. I was given RA in the question to be 0.1. So 0.1 plus RB. Now how do I find my E? You know that E is equal to K phi omega. But I don't know K phi. But I also know that E is equal to V minus IA RA. Right? I also know this. So I know my V is 220. I found my IA. IA is what? IA is 103.6 times RA. 0.1. So this is the E for the motoring. But that will be the same E, because I know that when I reverse the V, the E doesn't change initially, right? Because the speed remains constant. So it means the E will be constant. So if I'm able to find the E here, it's the same as the E at this point. So my E will give me 209.67. And that's the E output here. That's the E output there. So in the end, I'll get negative 206 is equal to negative 220 minus 209.67 over 0.1 plus RB. So here I can bring the minus out and to take away this minus here. So I get 0.1 plus RB being equal to 220 plus 209.67 over 206.12. 206.12 here. 0.12. So when I simplify this and subtract, so RB will be minus 0.1 here. I'll get my RB to be 1.98 ohms. My IB is 1.98 ohms. 1.98 ohms. So that's it for the first part of the question. That's it for the resistance that will limit the current to twice the rated value. Now the B says that determine the initial breaking torque. So determine the initial breaking torque here. Now we know that torque is proportional to current, right? So it means that the initial torque, let me call it T1. T1 over, so over here I can say T is equal to Ki. So T over I is equal to K. T over I is equal to K. So this means that T1 over K1 is equal to T2 over K2. So T1 over I1, is equal to T2 over I2. So this T2 is my breaking torque I want to find. Let me call it TB. Right, and that occurs at IA2. This is T1 at IA1. Right. So it means that from here I can write that. Okay, let me clean this side. So from here I can write that TB is equal to IA2 over IA1 times T1. I know that my IA2 is 206.12. IA1 is 103.6 times T1. So let me find what my T1 is. T1 will be the what? T1 is the initial torque. right? I know power. Power is given by what? Torque times the speed, right? Power is given by torque times speed. So I know that my torque will be equal to power over speed. So let's check if I have these values. So I was given the speed, the rated speed to be 1,200 rev per minute. 1,200, and I know that the output power of the motor is what, 20k. So I'll do 20k over 1,200 in rev per minute. So this will give me my torque. So this will give me my initial torque as 159.15. So I'll just put that value here, 159.15, and that'll give my braking torque to be equal to 318.3 Newton meter. So that's it. So you see, you can think about it like process wise, and that makes sense, right? Okay. So that's it for the B part. The C states that find the motor torque when the speed of the motor falls to 400. So I'm still using the fact that the torque is equal to IA2 over IA1 times T1. Don't forget that when the speed falls to, and when we move to a new speed, okay, that will affect the E. See, we know that IA2 is what? Minus V minus E over RA plus RB, right? So the new speed will affect the E, because E is equal to K phi omega. And that E will also affect IA2. So let me find the E at the new speed. So I know that from here I can also say E is proportional to speed. So here E1 over omega 1 is equal to what? E2 over omega 2. Right? So I can say E2 is equal to what? Omega 2 over omega 1 times E1. So the initial speed is 1,200. Now they said to limit it to 400. And the initial EMF I got 209.7. So this will give me a new EMF of 69. No, yes, omega 2. The omega 2 is the 400 here. And the omega 1 is the 1,002. This will give me 69.89. So I'll put that E here. So I'll get minus 220 minus 69.89 over RA, and I got my RB to be 1.98. So I put it inside. And once I have this, I can find my current to be 139.37. And so for this current here, I can now come and put that current here over IA1. So I'll get 139.37 over IA1 is 103.6 times initial torque 159.15. That'll give me the new braking torque as 214.72. 214.72. So that's it. So that's it here. So that's how this question is solved. Okay. That's how you got about this question. Okay. Yeah, so kindly take time to do all these reading parts. Nothing different from this part is even similar to like everything we read already. It's like it's repetitive, so you just take time to read it. Okay. And the next thing is the induction motors. With induction motors, all the formulas for induction motors hold. All the formulas for induction motors that we saw, that we know that okay, torque for induction motor is given by 3 over omega s multiplying V1 squared over, let me see. So all the formulas hold, okay. Times R2 prime over S. I've forgotten what goes down here. Okay, I think it's r1 plus r2 prime over s squared plus xe squared. Yeah, I think it's this here. I think maybe square root here. Also. So just all the formulas for induction motors hold. Okay. Okay, so there's no square root there. So there mustn't be a square root here. There must be a square root here. So yeah. So all the formulas hold. Yeah. So now let's see. So the characteristics for induction motor is this. Is this. Right? Remember that here we perform it for all the quadrants, so it extends to this point. So for a bidirectional torque load, I can have it a braking occurring here, right? Yes, I can have a braking occurring here. For unidirectional torque load, if I have it like this here, unidirectional, so here the braking must occur in the 4 quadrants. So I must reverse the terminal so that I can have it cutting it at this region here, and then I can have my braking occurring at this region here. Okay, so that's it. Okay, sure. That's so for the unidirectional torque load, you must reverse it at least 2 of the leads. So like I have the characteristics like this, and then you have the braking torque here. Or bidirectional, now you don't type the leads, so you just occurs in the 2nd quadrant. Okay. So there's the question here. All right. So a 208 volt 6 pole 60 hertz star connected induction motor has the following parameters. I've been given R1, R2 prime, XE. The motor is loaded by a 30 Newton meter bidirectional constant torque. If the load torque is reversed, because it's bidirectional, you should know that the load torque will be reversed. Calculate the motor speed. So we know that for induction motors, the motor speed, which is omega r, is given by synchronous speed multiplying 1 minus slip. So the first thing I'll do here is to find the slip, right? So I must find the slip here and use that slip to compute my speed. So now how do I find the slip? I know that T is given by VL, line voltage squared, over omega s multiplying R1 R2 prime over s squared plus xe squared times R2 prime over s. So from here, I was given the torque. I know that the torque will become negative because I'm doing the braking, right? For bidirectional load torque, so the torque becomes negative. I know VL. I can find my synchronous speed. Synchronous speed is what? Is 120 F over P. NS. So I know R1, R2 prime. So I can compute my S. So over here, I'll make the S the subject. So that's what, please kindly take time to derive it. So I'll make S the subject here, right? So put in all the values and multiply. So when you do that, you arrive at 25.36 S squared plus 5.07 S plus 0.16 is equal to 0. So when I solve this quadratic, I'll get 2 slips. I'll get my first slip to be negative 0.039. My second slip to be negative 0.161. Right now, the characteristics looks like this. Okay. So now what you must know is that, assuming the braking is occurring here, this is my synchronous speed here. Then the motor speed settles at this region here, omega r, right? It settles at the omega r here. So now the slip, it has a small slip. So between these two, I'll choose a relatively smaller slip. So I'll take this one here. So I'll say that my omega r is given by omega s, which is 120 f over p, right? 120 f over p. So I know how to compute that. 120 f 60 over number of poles 6. Change it to rad per second, 2 pi over 60. Then I'll do 1 minus negative 0.039. So I get my omega r. Let me see. Okay. So I'll get my omega r to be. Okay, so I'm changing it to rad per second, right? But they use rev per minute. So let me just find rev per minute first. Let me find it in rev per minute first. The synchronous speed is what is 120 f over p. 120 60 over number of poles 6. So that give me 1200. So my omega r is 1200. 1 minus 0.039. So when I multiply this, I'll get my omega r to be 1247 rev per min. So that's the first part. So I can change to rad per second. That's the A. Then the B says that what? Find the power delivered to the electric supply. So to find the power delivered to the electric supply, say I have a motor, I have an electric supply. Let me realize it. I have an electric supply here, right? P electric. I have a motor power output. There will be some losses here. So to find the electric supply, I must find the motor power and the losses and sum them together. That'll give me the electric supply. So that's what I'll do. So first thing is to find the motor power. And that P is equal to what? Torque. It's torque times speed, right? So to be equal to the torque at this region here. So let me call that the braking torque times the speed, omega r. Times the speed over that point, which is the omega r. So the torque is what? The torque is 30 Newton meter. But don't forget to say reverse, so it becomes negative 30 times the speed in rad per second. So times 1247 times 2 pi over 60. So that'll give me the motor power to be negative 3.918 kilowatt. Negative 3 points. So I'm cleaning this side. Negative 3.918 kilowatts. Negative 3.918 kilowatts. Now, next is to find the rotor losses. Rotor losses is equal to slip over 1 minus slip times the motor losses. So that's it. So the slip was negative 0.039 over 1 minus 0.039 times PM. PM is negative 3.918 kilowatts. So I'll substitute everything inside the equation, and I'll get the PJR, which is the rotor copper losses, to be 0.1471 kilowatts. Now that I have my PJR, I can find my PSR, which is the stator copper losses. PJS, sorry. That one is always given by R1 over R2 prime PJR. So I was given R1 to be 0.6. R2 prime was given by 0.4. So multiply this by PJR, that's 0.147. 0.147. And that will give me a value of 0.2207 kilowatts. So I can now find my total losses. So my total copper loss will be equal to what? To be equal to 0.1471. plus 0.2207 kilowatts, and that will give me 0.3678 kilowatts. 0.3678 kilowatts, right? So now the power supply to the electric source is given by the motor power, right, which is negative 3.918 plus the losses 0.3678, and that'll give me negative 3.550 kilowatts. So this negative here implies that the power is rather supplied. We saw that during breaking, the power is supplied back to the supply. So that's what the negative implies. So our answer is correct. So that's it. All right. So that's it. Okay. So anyway, there's a reading. You kindly take your time to read. Okay. So another thing you must know. Another thing you must know. Another thing you must know is that for plugging, the slip is equal to 1 plus omega r over omega s. And so this plugging in synchronous in induction motors. For regenerative braking, for rheostatic braking, sorry, the slip is omega r over omega s. So these are things that you must know. Okay. But for regenerative, the slip is the same, is what we know. Omega s minus omega r over omega s. So this for regenerative, this for rheostatic, and this is for plugging. So kindly take note of the following. Okay, sure. Okay. Now, in the rheostatic braking of induction motors, okay, we do something called DC excitation, right? So you connect the DC to the terminals to generate the field, okay, the stator field. So now we want to find the equivalent AC that will give us that same magnitude of DC stator field, right? So that's what this chapter is about. Yeah, we want to find the equivalent. We want to find the equivalent AC excitation. Okay, so we consider 3 or 4 widely used star connections, stator connections. Sorry. We assume that the space EMF produced by the DC is in the phases are sinusoidal. So you want to find the corresponding. So over here, what you must know is the formula at the end. So you must know that if I have star, right, and then I apply the DC to 2 leads like this, then IAC is equal to square root of 2 over 3 IDC. So this is VDC, some direct voltage, which would cause some direct current to flow through. I want to find the AC equivalent, which will be given by this. If I have it like this, if I connect it to the 3 leads, if I connect all the 3 leads like this, I put my voltage here, VDC here, then my IAC becomes what? It becomes root 2 on 2 IDC. So here is the formula. So just know how it affects the formula. If I have delta here like this, and I connect it to 2 leads like this, VDC here, the IAC is equal to root 2 over 3 IDC. And if I have delta, same delta, and I connect it to 3 leads like this here, VDC, then my IAC is equal to root 6 over 6 IDC. So that's it here. So that's what you must know. So it's derived, but then what you must know is the formulas. What you must know is the formula, the final equations. So that's it here. You can see the currents there. Okay, so you kindly take time to read through. Just read through so that you know what's going on. Okay. Now the final thing for us to find, which are also formulas, which are also formula work, which is also a formula work, is the, kindly hold on for me. Final thing for us to find is the energy. Is the energy relations during breaking. Energy relations during breaking. Energy relations during breaking. Okay. So here is formulas. Know that if you are performing rheostatic braking, they are derived. So just take your time to go through the revision. Rheostatic braking of DC shunts, right? Or separately excited. The energy lost in the armature windings, the energy dissipated in the armature windings, so energy is equal to the kinetic energy. So this is the energy that's lost in the armature windings. If I take plug-in, the energy lost is given by 3 over 2, so 3 times the kinetic energy. Okay, so this is for DC shunt. Now let's take induction motors. If I take induction motors, for the induction motors, there will be rotor and then there will be stator losses, right? So for the induction motor, first thing is to find the rotor losses. So the rotor losses, which is the omega ER, is equal to J omega S squared over 2 S1 squared minus S2 squared. So this is it. Right, this is how we compute it. Okay. So this for plug-in. So for induction motors, this is the plug-in formula here. Then if I take the rheostatic braking for induction motors, okay, so this is in the rotor. So let's find it for the stator too. Omega ES. Omega ES is the same as this, right? Except you multiply by R1 over R2 prime. So J omega S squared over 2 S1 squared minus S2 squared times R1 over R2 prime. So that's for plug-in. If I take rheostatic braking, my omega ER is given by j omega s squared over 2, and my omega es is equal to 3I squared times the AC equivalent of the DC times R1 times TB. This TB is like a time for breaking. R1 here. And we have everything here. So you have to know these formulas. Okay. So let's take the last example. Let's take, under this one, there are 3 examples. Let's just take one of them to show that we understand what we are doing. So you see all the formulas are derived. So just find the formulas. Okay. Let's try this example here. So we've been given a 10 kilowatt 3-phase 400 volt 20 amps 50 hertz 960 revolutions per minute 0.88 power factor screw cage induction motor drives a certain load. The total moment of inertia of the driver is 0.5 kilogram meter squared. Determine the number of starts per minute that this drive can make under no load conditions without exceeding the total power. The first thing you must find is to find the full load losses. First, find the full load losses, which is equal to electric power minus motor power. So let's find electric power. It's equal to root 3 VL IL cos phi. So that's root 3. We're giving VL in the question as what? VL is 400, right? IL 20 cos phi 0.88. So that'll give me electric power of 12193.6 watts. We know that the motor has an output power of what? 10 kilowatts. So PM is 10 kilowatts. Therefore, the full load losses, which I want to find, full load losses, will be equal to what? PE, which is 12193.6 minus 10,000. So that'll give me 219.6. 2193.6. These are the full load losses, right? So if I want to find the energy, this is power. I want to find the energy loss in 1 minute. So energy lost per minute. Energy loss per minute is what? Multiply this by 60. So that's 2193.6 by 60. So this is the first value you find. Energy lost per minute. Now let's also find the energy lost at starting. We said that for the induction motor, the energy lost at starting, the formula is given by half j omega s squared S1 squared. No. So check the formula here. So half j omega s squared 1 plus R1 over R2 prime. R1 over R2 prime. Now I was given j. I can find omega s. 120 f over p. And then multiply by 2 pi over 60. Let me find, how do I find my R1 over R2 prime? So assume the ratio of R1 to R2 prime is unity. So take here to be 1. So I'll be left with half times the J was 0.5 times 120 F over P. So that's 1000 over 60. That's me changing it to rad per second. Times 1 plus 1, 2. So that'll give me 5483 joules. So this is the energy loss during starting. Energy loss during starting. Energy loss during starting. So the number of starts that we can make. So number of starts is equal to full load energy loss. Full load energy loss divided by energy loss during starting. Energy loss during starting. So that will give me full load energy loss. 2193.6 times 60 over energy loss during starting. 5483. So that will give you 24. You get 24 points. See. So when you do that, you get 24 points. Let me see. Let me simplify it. So I'm doing 2193.6 times 60 over 5483. Okay, here you get 24.00. But I just know that no matter the number of decimals, no matter what decimal points you get here, you always round it to a lower value. So even if I had gotten 24.99, I'll still round it to 24. So that's one thing you must know at the side. That brings us to the end of the chapter 3. So take your time to do the reading part. Then Mariam says that, as a TA, Mariam, she says that when we solve, you see, she has sent some 2 trial questions, trial 1 and trial 2. When we go through those questions plus the questions was sent, we should be fine for the midterm. So she says she will drop the answers to the trial questions tomorrow or the day after tomorrow for us to go through. Okay, so just read through and then let's keep our fingers crossed. We'll be fine. Okay, thank you very much. Thank you very much. And have all the best in the exams.